Lecture 14 covers sections 5.3 through 5.4. At the end of today's lecture, you should be able to identify a reversible and irreversible process, and you should also understand the factors that contribute to irreversibility. For us to begin, we are going to talk about an ideal process. An ideal process is also known as a reversible process, and this is where we go from an initial state to a final state, and then from our final state back to our initial state. In doing such, there is no change to our system or surroundings. This is a purely hypothetical system, and we will show why this is purely hypothetical in a minute. Now, the opposite of a reversible process is an irreversible process. This is one where our system and or surroundings cannot be restored to the initial states after the process has occurred. For instance, let's consider a piston cylinder device that we allow air to expand from a high pressure and small volume to a low pressure and large volume. Then we recompress the system back to its initial volume. If it was an ideal process, the amount of work we gain through our expansion would be equal to the amount of work we put in during our compression. However, in reality, there's going to be friction associated with the piston ring between our piston and cylinder wall that is going to require a little bit more work during our compression process, and it takes away a little bit of the work during our expansion process. This is going to contribute to friction, which is going to result in a little bit of heating of either a system or surroundings, i.e., a real process is what's actually happening in most of our thermodynamic systems, where an ideal or reversible process is our hypothetical or theoretically best process. Some hypothetical reversible processes are as follows. Say we have a pendulum in a perfect vacuum, and it's able to swing using zero friction bearings between the pivot and the arm. Now, we'd assume that this could swing indefinitely. However, this breaks our perpetual motion machine of the third kind. We could also consider a gas in a perfectly insulated, frictionless piston cylinder device that is compressed then expanded. This also breaks a perpetual motion machine of the third kind. And we saw that this was the basis for idealized or reversible process that we then disproved by considering friction. There's many factors that contribute to irreversibility, and we are going to name just a few, the most common that we encounter in engineering applications. And the first is friction. Anytime you have sliding objects in contact with one another, or flow of a fluid, we dissipate energy. That is, kinetic energy of our sliding objects is converted to thermal energy. Consider the brake pads and rotors on this Lamborghini. During hard braking, the kinetic energy of the car is converted to thermal energy within the brake rotors that then is dissipated to atmosphere. We cannot recover this energy, and therefore it constitutes as a loss. This is an irreversibility. Additionally, anytime you have fluid with any viscosity flowing, the viscosity, i.e. resistance to motion, is going to dissipate energy of that fluid. Unrestrained expansion of a gas or a liquid to a lesser pressure constitutes as an irreversibility. Say we had a membrane separating air and vacuum, and that membrane ruptures. Our air is going to fill the vacuum, and the pressure of our system is going to be less than the pressure that the air was initially at. Through this unrestrained expansion, those air molecules are going to collide with one another and dissipate some of their energy. This is going to be an irreversible process. Anytime we have heat transfer through a finite temperature difference via conduction, convection, or radiation, we're going to have irreversibility associated with our system. Recall, conduction is a transfer of thermal energy through a material through vibrational waves. That is, as our molecules vibrate and pass thermal energy through our system, there is going to be a loss. So anytime we have heat transfer from a high to a low temperature, we're going to have irreversibility associated with it. Even if we have a refrigeration cycle where we transfer heat from a low to high temperature reservoir, we're going to have irreversibility associated with those heat transfer processes as well. And the last mechanism is any chemical reaction, mixing a matter with different composition or states, Joule heating, or inelastic deformation. Anytime we have a chemical reaction, we cannot take the resultant materials, put them back together, and form our initial material. If we have mixing of matter at different compositions or states, we're going to have irreversibility associated with either heat transference or phase change. Joule heating, i.e. the localized heating of a material as it carries current, is also going to be an irreversibility. That heating occurs due to collision of electrons that are now converting their electrical energy into thermal energy. And anytime there's an inelastic deformation in a material, some of that energy resulting in the inelastic deformation cannot be recovered. Thus, we have an irreversibility.